Well, I'm glad somebody was enthusiastic there.
I'm so excited.
I know, I could tell.
Can't wait to learn more math.
More math, more math.
Woot woot.
It's not all bad, really. Okay, continuing. Can we see my screen? That's the next question.
Yes, ma'am.
All
Yes,
right.
ma'am.
Great, great, great. All right. Probability can be considered in one of two ways. The first one is called empirical. This is where we use actual experimental data. So empirical probability means I'm going to use the actual values from an experiment to calculate the probability. For example, if I tossed a coin 20 times and got 12 heads and 8 tails. And I want to find the probability of heads. Okay, from our previous notes, the way we find probability is to look at how many times did it occur over how many times total possible. So if I'm looking for the number of heads from my experiment, heads occurred 12 times. How many total could it have occurred? Would be how many times did we toss the coin? So that means the probability would be 12 out of 20 for the probability. Now, anytime we're doing probability, we always want to reduce that fraction, and you want to reduce it to lowest terms. So that means that final answer would be 3/5. Now, suppose the question had been to find the probability of tails. We still have that information. The number of tails was 8 out of a total of 20 tosses, which means that reduces to 2/5. So when we're doing empirical probability, we are using the actual values from an experiment in order to find the probability. The second kind of probability is theoretical. And in using theoretical, we use accepted rules that have been based on the theory of past experiments. So we know a coin has two sides. It's either heads or it's either tails. So in theory, the probability of getting a head can't spell now. Should be 1 out of 2 choices. I can only get a head once out of the 2 possible choices on my coin. But in that experiment, the head occurred 12 out of the 20 times. So that answer was different in theory than it was in the experiment. And that is possible. Theoretical and empirical can be different answers. But that is because of what we call the rule of large numbers. "20 tosses is not very many tosses. If I continued tossing that coin many, many, many more times, hundreds of times, the more times that I toss the coin, the closer it would get to the theoretical amount. So the rule of large numbers guarantee us that our empirical data will eventually reach the theoretical values. Now let's look at some notation that we can use to help abbreviate some of this writing that we're using, the probability of heads, instead of having to write that out in words so much. We can name an event. We can use any capital letter. So we can name an event say T for tossing the coin. We can use T with an apostrophe to indicate not an event. So just like with sets, we can see that same terminology come into play. But we can also see this symbol, this little squiggly line, a simile, to mean not event. So if I want to indicate the probability of an event, I would write P and the name of the event in parentheses. And if I wanted the probability of not the event, then I would have P, T with the apostrophe, or the probability of not T. And again, just to summarize, we can write probabilities as a fraction, as a decimal, or as a percent. If there is no direction given, you would always write it in the fraction form. So that's your standard rule. If no direction is given to indicate differently, give your probability in the fraction form. And when you give it in fraction form, it should always be in simplest form. Now, as a little review, in case this is a little rusty for you, if you had the fraction 1/2, can you go from the fraction to the decimal to the percent? So remember, you divide. 1 divided by 2 gives us the decimal. So that would be 0.5. To change a decimal to a percent, we multiply it times 100. So 0.5 times 100 gives us the percent, which is 50%. When I multiply it by 100, I'm moving the decimal over 2 places to the right. In reverse, if I was given the percent, to change it from percent to decimal, I divide it by 100. Or I'm moving the decimal to the left 2 places. And so I get 0.2. To change a decimal to a fraction, I take the decimal, that's 0.2 or 2/10, and then I reduce the fraction to be 1/5. So that's just a quick little review, going from fraction to decimal to percent, percent to decimal to fraction. So if you're a little rusty in that area, you might want to spend some time on your own going back and building those skills up a little bit if you're a little rusty in that area. Now, let's look at a couple of more percent problems. Just simple percent. Excuse me, not percent problem, simple probability. Had percent on my brain. Simple probability problems. These will be similar to the types of problems you might see on some practice problems. So for example, you have a coin that is tossed 100 times. It landed on heads 44 times. First question, is this empirical or theoretical probability? Is this going to be empirical or theoretical probability? Do you have an experiment? Do you have actual data to use? You do have an experiment, so that makes it an empirical situation. Second part of the question is to find the probability. What is the probability of heads? Well, in this particular problem, heads occurred 44 times out of how many tosses total? 100. So how many times can it occur over how many possible? Well, there's my fraction, but I always reduce it. So what is 44 over 100 reduced? That would reduce to 11 over 25. Now, this particular problem doesn't specify it, but suppose it said write it as a decimal. I would divide 11 divided by 25, which would be 0.44. What would be that same answer as a percent? I multiply that by 100, and that would be 44%. So 44% of the time, when I tossed that coin, it landed on heads. Now, what would be the probability of tails? It doesn't give me the information for tails, but can I find it? If it landed on heads 44 times, how would I find the tails? How would I find that? I would subtract 100 minus 44. What would that be? $100 minus 44. That would be 56, wouldn't it? If it didn't land on heads, it had to land on tails the other times. And so my probability for tails would be 56 out of 100. I would reduce that, and that would be 27 out of 50 times. And I could go through and find the decimal and the percentage as well. Any questions on that problem? Let's do one more. We have a drug company. They're testing their new drug on 500 volunteers. 379 observed a weight loss. "62 observed no weight loss. And 59 observed increase in weight. Is this empirical or theoretical probability? Empirical or theoretical? Are we going to be using experimental data, or are we going to be using theoretical rules? We're using the actual data of the testing, right? So that means it would be empirical. Question B. The probability of success for this drug testing. How many observed weight loss? 379 people. How many could observe weight loss? How many were in the study? How many took the drug? What was that total? That was 500 volunteers. So my probability is how many could over how many total. If I can't reduce that fraction, so that would be my final result, but I can change it to a decimal, which would be 0.758. And that decimal as a percent would be 75.8%, which makes a little more sense in this particular study. This drug has a 75.8 or 76% success rate, which is pretty good. Excuse me. So what's the probability of success? It is fairly likely to have success. It's not super close to 1 on that probability number line, but it is relatively close to 1, so it has a pretty good certainty of having success. So we've looked at problems to see simple probability. We've looked at how to use the notation We've looked at how to change from fractions to decimals to percents. We've looked at how to compare the answers and think about what's the likelihood of that success rate. So there's lots of things tied up in those particular problems. Any questions on what we've gone over there?
Can you do an example of a theoretical one?
Of a theoretical one?
Yes, please.
Okay. Are there okay, my screen has hung up on me. It is not showing my screen. Can't get it back to that. All right, can you see the screen now? Yes? All right, good. All right. Notice this time in the example, it doesn't give us a lot of data. It only asks, if we had a coin toss, what is the probability of tails? So is that empirical or theoretical? And that is theoretical. So the probability of tails would be tails can occur once out of either heads or tails, so two possibilities. Let me actually give you another example as well for theoretical. We're going to draw a card from a deck of 52. What's the probability that it's going to be a diamond? So if we ask ourselves, is that empirical or theoretical? There's not a lot of data given. It's only the situation about drawing from a deck. So we're going to have to rely on theoretical information to make this prediction. So the probability of being a diamond means that there are 13 diamonds in our deck of cards. There are 52 cards in the deck. So the theoretical probability is 13 being diamonds out of the 52 cards is going to reduce to 1/4 for the probability. So I hope that helps in the difference between empirical versus theoretical probability. All right, the next step that we're going to look at is to focus on sample space. We've looked at finding some basic probability problems, but the next thing that we're going to focus on is sample space, which means we're looking at finding the set of all possible outcomes. In a sample space, we want to find all the possible outcomes. And in probability, that is the first thing that we want to be able to do. So in probability, finding the sample space is one of the first things that we have to think about. It is one of the first things that we have to consider. Now, if we are tossing a coin, the sample space is pretty easy. It's either going to be heads or tails. So there's not a whole lot to consider when we're tossing a coin. Sample space is either heads or tails. If we're rolling a die, the sample space is going to be, when you roll it, it has 6 sides. So they're numbered 1, 2, 3, 4, 5, or 6. Now there are other kinds of die. There are hexagon dies. There are tetragon dies. But in general, when we talk about a die, we're going to talk about a 6-sided die. If you have 2 die, then we're going to talk about the outcomes of rolling 2. And a lot of times we have to write that outcome in pairs. So we can roll a 1 with a 1. And sometimes we put parentheses with them to indicate that roll was a 1 with a 1. Or we have a 1 with a 2 on the second roll. Or we could have a 1 with a 3 on the second roll. And we could have a 1 with a 4 on the second roll. A 1 with a 5 on the second roll. A 1 with a 6 on the second roll. And then we could have a 2 on the first roll with a 1. And then we could continue that table, a 2 with a 2, and so on. So we could get a long table, and we would get 36 outcomes when we have 2 die once we created our table. A 3 with a 1, a 4 with a 1, a 5 with a 1, and a 6 with a 1. Now, I'm not going to complete the table. You can complete that table on your own. But those would be all your possible outcomes. And sometimes it is helpful to have that table in front of you as you are doing probability problems. If you're not familiar with rolling a die, having that information in front of you can be helpful. So it could be helpful for you to complete that table, to have that to look at. You can also find that table in Chapter 11 in your textbook to look at as well. Now, the outcomes with a deck of cards. For some of you, you're not very familiar with a deck of cards, so just to review a little bit with a deck of cards, there are 52 cards in a deck. We're using a standard deck of cards. A lot of decks come with 2 jokers, but we're going to exclude the 2 jokers. There are 4 suits of cards in that 52 deck. The suits are hearts, spades, diamonds, and clubs. There are 13 cards in each suit. The suits go from ace to kings. The ace is usually considered in place of the 1, but for those of you who play cards, you know ace can be considered high or low. Sometimes the ace is used up with the king, higher than the king, but a lot of times in terms of just looking at the placeholder, ace is like a 1, and then they go 2, 3, 4, 5, 6, 7, 8, 9, 10, and then you have jack, queen, king. So for some of you who may not know that, jack, queen, king are considered your face cards. So a question in probability might be, what's the probability of drawing a face card? So you would need to know which ones are your face cards. For some of you who may not know that, there are one-eyed jack versus two-eyed jacks. So there are two one-eyed jacks in a deck. So that might be a question that comes up in probability. So I just wanted to go over a deck of cards, especially for those of you who have not played cards. You may not be familiar with what is in a deck of cards. So I wanted you to know what the possible outcomes could be for a deck of cards. Sometimes if you're doing picking items out of a bag, it might be like a bag of marbles. And it will have to give you what's in the bag that you're selecting from. So it might tell you that you have 2 red marbles, that you have 4 blue marbles, you have 1 white marble. And so your sample space would be red, red, blue, 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 and white. So again, you want to be able to determine what is your sample space depending on the situation that you're dealing with. So these are just some examples of different situations that you typically encounter with probability questions. And I wanted to be sure you are familiar with the sample space involved in determining the sample space for those situations. Now, the next question is, what are ways to find sample space? If you are not familiar with sample space, how do you determine what the sample space is? You might use a list, just like we did with some of the cases up here. You might use a table to organize it. So using this method with the 2 die, you could put that information in a table. Some people guess, oh, that sample space might be this. That's not a very effective way to determine sample space, but it is a technique. Some people use trial and error. Okay, I'm not sure what it might be, but I'm going to try this. And that is a method to find out or figure out what's in the sample space. Another way to figure out sample space is to use what we call a tree diagram. And we'll look at that in a moment. Another technique is using what we call combinations or permutations. And fundamental counting method. So all of these are ways to find sample space. Some of these methods just give us how many. Some of the techniques tell us what is in the sample space. So each technique has an advantage over the other. If you just want to quickly find out how many items are in the sample space for that total, one method might be better than the other. If you want to find out exactly what the sample space is, then another technique might be better. All right, so we've looked at making the list and making the tables. Let's look at the fundamental counting method. The fundamental counting principle can only tell us how many is in the sample space. It doesn't tell us what's in the sample space. It can only tell us how many is in the sample space. So Sally has 3 shirts, 4 pairs of pants, and 2 scarves. How many outfits can she make for work? So the fundamental accounting principle tells us that we can just multiply the number of each of those items, 3 times 2 times 4. So 6 times 4 would be 24. So she can make 24 outfits, or 24 different outfits for work. It doesn't tell us what matches up with which, but it does tell us she can make 24 different outfits. If we wanted to know what specific outfits, we would have to have shirt 1, shirt 2, shirt 3. We would have to have pants 1, pants 2, pants 3, pants 4. We would have to have scarf 1. I'd have to label that something else, SC1, SC2. And then we would have to make the combinations, okay? I would put shirt 1 with pants 1 with scarf 1. That's one combination. I would put shirt 1 with pants 2 with scarf 1. That's another combination. And I would have to go through and continue that list to figure out what the outcomes are. But this tells us how many very quickly. So all the fundamental counting principle does is tell us how many outcomes there are. It does not tell us what the outcomes are. Okay, let's look at a tree diagram. The tree diagram will be able to tell us how many outcomes and what the outcomes are. It will be able to tell us both. So we want to figure out how many outcomes there are when we toss a coin 3 times and what they are. So we start with our diagram with the first toss. And with the first toss, we start our diagram with a branch. We can either get heads or tails on our first toss. Then we look at our second toss. From our first toss, we branch from the heads. From that head, we can either get heads or tails on the second toss. From the tail, we can either get heads or tails from that toss. So notice our tree diagram. Our tree is branching off and expanding. That's how it gets its name, tree diagram. And then we do the third toss. So from each of these branches, we branch again. We can get a head or a tail from that first one. From this one, we get a head or a tail. From this one, we get a heads or a tail. And from this one, we get a heads or a tail. So we've tossed once, twice, 3 times. To find the number of outcomes, we're going to count the number at the end. There are 1, 2, 3, 4, 5, 6, 7, 8. So if we count up all of those on the end, that gives us the total, 8 outcomes total. Now the next thing is, what are the outcomes? We can also get that from the tree diagram. We follow the branches to do that. So from this first branch, we go head to head to head. So that is one of my outcomes. Follow the branches, head to head to head. Then I follow the next one, head to head to tails. And then I do from head to tail to head. And then I follow head to tail to tail. And so that takes care of this first little branch up there. And so now I use the tail branch. So tail to head to head. And then tail to head to tail. And then I do tail to head. and then tail to tail to tail. And there are 1, 2, 3, 4, 5, 6, 7, 8. That number should match my total outcome. So this tells me what the outcomes are, and it should match the same number as the outcomes. So if my question was, what is the probability of 3 heads? When I look at all my possible outcomes, how many times did 3 heads occur? It occurred once. Out of how many total outcomes? 8. So that's how I can do my simple probability based on finding the sample space using my tree diagram. So we've looked at finding fundamental counting principle to find out how many outcomes. The tree diagram tells us not only how many, but what the outcomes are. And next, we're going to look at combinations and permutations. Permutations is a method to find the number of outcomes when the order matters. For example, if I wanted to find out how many different ways to find the officers in a club, president, vice president, secretary, that's an order. It makes a difference who gets what office in the club. That's an order. If we're running a race, first place, second place, third place, the order matters. That makes it a permutation. So when the order matters, the problem is a permutation. The notation can be written in lots of different ways. It can be written as the permutation of n selected R ways. It can be written as n permutation R, n selected R ways. The formula to do a calculation for a permutation is to use n with a little exclamation mark on top over n minus R with an exclamation mark. Now, as a side note, the exclamation mark means factorial. So if I have a problem that says 4 factorial, that means that I take whatever this number is and I multiply it times each succeeding number down to 1. So 4 times 3 is 12, times 2 is 4, times 1 is 24. That would be how you would calculate a factorial. So in this formula, that means we're doing n factorial over n minus r, you do the subtraction first, factorial. And if you get 0 factorial, that answer is 1. Now this is where you're going to start needing your calculators. So if you haven't purchased a calculator, this is where you need to get one. You need to either borrow one or you need to go out and get one of those TI-30 calculators for about $20. So you're going to need to have this handy as you start these calculations. There is a key on your calculator, whether it is the TI-84 calculators, if you already have that, or the TI-30s that has this little symbol on the calculator to use. So it's important that you see that and know how to use it. So here's a sample problem. If we want to find the permutation of 6 items chosen 4 ways. That means it would be written 6P4. Now, I don't have a TI-30 calculator, but I have a TI-84. So I'm going to show you this calculation on the TI-84. Let me first set it up in the formula. If you don't have a calculator, you're going to have to do it the long way. So that just means we're going to do 6 factorial over 6 minus 4 factorial, which means we have 6 factorial over 6 minus 4 is 2 factorial. And then you're going to have to calculate the top and calculate the bottom and reduce it. And you should end up with 360 when you finish. Now, if you have your calculators, you have to type the first number first. So we're going to type the 6 first. Even if you have a TI-30 calculator, you still have to type that 6 first before you press the key. On the TI-84, you're going to press the math key. You're going to then press the arrow keys to go all the way over to probability. And then you're going to select the second choice. And then you type in the 4 and press enter, and it gives you the result. Everybody see that? If you have the TI-30 calculator, you type the 6 in, you press that key with that function on it. You might have to press a shift key to get that. And then you press the number 4 and then press enter. Either way, you should get the answer 360. If we wanted to do 5 items, selected 5 ways. That would be 5 selected 5 ways. In the formula, that would be 5 factorial over 5 minus 5 factorial, which is 5 factorial over 0 factorial. So remember, 0 factorial is just 1. which is going to give us 120. So using the calculator, 5 math over to probability, down to choice 2, put in 5, and enter. So again, you're going to have to practice with your calculators in order to know how to use them. Okay, the last one is combinations. A method to find the number of outcomes but the order does not matter. So let's say we had 8 letters. To arrange 5 ways. Think of that as 5 spaces. We want to put the 8 letters in those arrangements 5 different ways. How many arrangements can we make with 8 letters? For combination, we denote that as C, N, R. So it looks very similar to permutations. Or it's going to be N, C, R. The formula is going to be a little different though. It's going to be N factorial over R factorial times N minus R factorial. So it has that little bit of extra there in the denominator. So going back up to our problem here, we're going to do 8 combination 5 ways, which means we would do 8 factorial over 5 factorial times 8 minus 5 factorial, which gives us 8 factorial over 5 factorial times 3 factorial. So you have to calculate each factorial separately and then multiply the 2 answers together. So 5 times 4 times 3 times 2, get that answer. 3 times 2 times 1, get that answer. And then take the 2 answers and multiply together. So be careful about that. On your calculator, similar to permutations, we're going to put the 8 in first, select the math key, go over to probability, go down to choice 3 this time, select it 5 ways, press enter, and that turns out to be 56. If you have a TI-30 calculator, you would put in the 8 first, select the key with the NCR on it. Again, you might have to press Shift first. I don't remember. And then enter your 5 and press Enter, and it should give you the same result. But if you don't have those calculators, I would strongly suggest going through this formula. You still should get the same answer, but it does certainly take a little bit longer to do that calculation. Any questions? A lot of stuff there. So we did a little bit of excuse me, go ahead.
I have a question.
Uh-huh.
About, so I don't have a calculator yet, but I'm gonna buy one. Could you maybe post videos of how you do this on the calculator so we can go back and look at it and do it on our own?
Okay. I'll be posting class videos today.
Okay.
They will come up later this afternoon, so it will have what we did in class today. And I think I have some links that I can put up as well for the TI-84. I don't know that I have links for the TI-30, but I think if you get the TI-30, once you see those keys on there, it's very similar in how you put the information in. Okay?
Okay. Okay, thank you.
So we went over a little bit about probability in terms of terminology, a little bit about how to calculate probability, and then a lot about finding sample space, a lot of stuff that's involved in getting to the probability. So your practice problems will involve a combination. Some things about finding probability, some things about finding permutations, some things about combinations, some things about doing a tree diagram. So it will be a mixture of things in your homework problems to try as you get those posted up. Okay, so I'll be posting the actual notes later today. I'll be posting a video of class today as well, so you can go back and re-listen to that information if you need to go back and re-look at that. And as I said, I'll be posting some short videos for you to go back and just listen to, and then take little short practice quizzes on about the concepts. These are different videos than what have been in class, but they should be helpful for you about the concepts about probability. And the little short quizzes will be from a site that is online, but I'll give you that information when I post the information about the video of how to get there. Okay? Any questions in terms of what to expect there? Okay, I will be traveling this weekend, so I will not be available over the weekend to answer many questions. So if you have something, you'll need to try to contact me tomorrow, or I won't be back in touch until late Sunday evening. So just keep that in mind if you're having trouble over the weekend, that I won't be in contact until late Sunday night or Monday after Friday. Okay. All right. All right. Have a great day, folks. Good weekend. Be safe.
Do we have any homework for this?
It will be posted later today.
Okay, thank you.
Mm-hmm.